Today we're going to follow on from our previous Kerberos overview and look at Kerberos Authentication in more detail. We're going to examine the messages passed between components and how different encryption keys we reviewed last time get used in practice. We will look at both the initial authentication of the user and how the user then authenticates to a service. I'm Stuart Rogers with SAS, and this is the Technical Insights and Expertise series. First, we will look at the process of authenticating the user. From last time, the messages here are the KRB-AS request and KRB-AS response. We start with the client machine and the KDC. Running inside the KDC are the authentication service, labelled AS, and the ticket granting service, labelled TGS. The first step is for the user to provide the client machine with their long-term key. Remember, this is associated with the password of the user. So, the user types their password into the client, or perhaps inserts a smart card, or provides a biometric. The client sends a clear text message of the user ID to the authentication service running on the KDC. This is the KRB-AS request. Ideally, the authentication service then responds with an error. It tells the client that it needs to pre-authenticate. So the error it sends back is that pre-auth is required. The client then takes the user's long-term key and uses this to encrypt an authenticator. As we discussed last time, the authenticator quite often includes a timestamp from the client. This authenticator, A, is now sent to the authentication service. The KDC looks up the user's long-term key and uses this to decrypt the authenticator A. Normally, this step will include comparing the timestamp to ensure that this is not an attempt by an attacker to replay a valid authenticator. Decrypting the authenticator A with the user's long-term key validates the user. With the user validated, the authentication service constructs two pieces of information to be sent back to the client. First, it generates a session key for the ticket granting service. Remember, the session keys have a short lifetime. This session key is then encrypted using the long-term key of the user, shown as B on the diagram. The other piece generated is the ticket granting ticket, C. Information in the TGT is encrypted with the long-term key of the ticket granting service, meaning that the client is unable to decrypt the TGT since it does not possess the correct long-term key. One of the important parts of the TGT is the same ticket granting service session key that was encrypted using the user's long-term key. So essentially, the TGS session key is sent in two different formats to the client. One format the client can access, the other the client cannot access. This will become important later when the TGS session key is used. Finally, the client uses the long-term key of the user to extract the ticket granting service session key from the KRB-AS response, B. One thing to note is that it is possible to disable pre-authentication. In such a case, we skip steps 3, 4, and 5. This removes some of the security provided by Kerberos and just leaves us relying on the fact that only a client with the user's long-term key will be able to extract the ticket granting service session key from the authentication service response. It is not recommended to disable pre-authentication. This completes using Kerberos to authenticate the user. Once the user has successfully authenticated to the authentication service running on the KDC, at some point in the future, they are then able to attempt to authenticate to a service. Now, we show all three heads involved in the Kerberos Authentication Protocol. We have the client with the end user, the server running the service the end user wants to connect to, and the trusted third party in the form of the Kerberos Key Distribution Center. Our Kerberized client is aware that for it to make a successful connection to the Kerberized server, it must request a service ticket from the KDC. This is a KRB TGS request and KRB TGS response set of messages. The client constructs the KRB TGS request message to request the service ticket from the ticket granting service running on the KDC. Included in this request is an authenticator A and the ticket granting ticket B. This time, the authenticator A is encrypted using the ticket granting service session key. As before, normally this authenticator will include a timestamp from the client machine. When the ticket granting service receives the request, it uses its own long-term key to extract the ticket granting service session key from the ticket granting ticket B. Then it uses the extracted TGS session key to decrypt the authenticator A sent by the client. As before, normally this includes a timestamp which the ticket granting service can compare to its current system time. This limits the chance of an attacker replaying a valid authenticator. Decrypting the authenticator with the TGS session key extracted from the TGT-B does two things. First, it validates the user. But also, since the TGS session key was sent in the request, it means that the ticket granting service does not need to keep track of session keys. So, essentially, from this perspective, the ticket granting service is stateless. It does not matter if this request for a service ticket is sent to a different KDC in a cluster to the initial authentication of the user. With the user validated, the ticket granting service is able to send the KRB TGS response. Included in the response is a session key for the service, which is encrypted, again, with the ticket granting service session key, shown as C, as well as the service ticket D. The service ticket D also contains a copy of the session key for the service, but the service ticket D is encrypted with the long-term key of the service, so the client will be unable to process the contents of the service ticket, since it does not possess the service long-term key. The client takes the part of the KRB TGS response containing the encrypted version of the service session key, shown as C. The client then uses its copy of the ticket granting service session key to extract the service session key from the message. Now that the client has both the service ticket and the service session key, it can send its authentication request to the service. This is the KRB AP request message. Contained in this message is the service ticket D and a new authenticator E. This time, the authenticator is encrypted with the service session key. Remember from last time, when looking at the network traffic, you may not see the KRB AP request message, as this is often wrapped inside the protocol used to connect to the service, such as the GSS API or Spinago. The Kerberos service then performs an action similar to that performed by the ticket granting service to validate the user. The service takes its long-term key and decrypts the service ticket. This gives the service access to the service session key created by the ticket granting service. With this session key, the service is then able to decrypt the authenticator sent by the client and validate the user. As before with authenticators, these usually contain a timestamp to mitigate replay attacks. The last two steps are defined in the Kerberos protocol as optional. The service can send a KRB AP response containing another authenticator. This authenticator is encrypted using the service session key. When the client receives the optional response, it can use its own copy of the service session key to decrypt the authenticator. If the client is able to use the session key to decrypt the authenticator, it proves the same session key was used to encrypt it. This in turn means the service was able to correctly decrypt the service ticket the client sent, and hence the client is assured the correct service was sent the service ticket. This completes our overview of Kerberos Authentication. In the next session, we will look at some more advanced authentication processes, namely both delegation and cross-realm authentication. For further information, you can see the following resources. For a definition of the Kerberos protocol, you can see RFC 4120 available here. And for a definition of the GSS API protocol, you can see RFC 4121 available here. And finally, Microsoft have published a great guide explaining how Windows implements the Kerberos protocol, and you can find that here. Hopefully, this has given you a better understanding of how the different Kerberos tickets and encryption keys are actually used. Having this understanding should make it easier for you to troubleshoot issues with Kerberos authentication. Thank you, and check back with your global enablement and learning team for more technical insights.